Bom dia a todos. Vamos começar a aula de hoje. So let's start. Okay, so yesterday we finished the proof of main theorem. It was a very topological and intuitional proof, but at the end, if you want, you can write down the details and you can make it very rigorous. So let's focus on one example of our situation. So the projective variety X that we took, let it be Pn plus 1. And then I will use the letter X for hypersurface, but so from now on you can forget this usage of not use X for Pn plus 1. And the coordinate will be x0 until xn plus 1. And there was this hyperplane section Z. I will put it Z equal to 0. This is another copy of Pn. Now remember that my notation has changed because now the variety X has dimension n plus 1. In the previous versions, the n was the dimension of X. You will see the reason why I'm considering this change of notation. So as you know, X minus C is a copy of Cn plus 1. And we took another hyperplane section, let's say Y, f equal to 0, and f a homogeneous polynomial of degree d. It was so this f that you see here is basically just a moment. So f x1 until xn is just substituting x0 equal to 1 x1 until xn plus 1. Okay. Okay. And in our proof, we use this map, and we prove that it is a fibration outside its critical values. Anyway, let's go further. Something that I will use it, that this polynomial f is no more homogeneous if you write homogeneous pieces of f0 constant, f1 degree 1, and then degree fi homogeneous. This is fi is homogeneous. Then the transversality condition that we use, so let's write it. Transversality hypothesis that we use, that then will be translated into the fact that fd has an isolated singularity at 0 in Cn plus 1. Okay, if you don't know what it is, it doesn't matter. Let me write some equivalent version. So one equivalent version is that this Cx. So from now on, I will write X for x1, x2, xn plus 1. So Cx, let's say the Jacobian. In my book, I call this one G because I have generalized it to this notion of a tame polynomial. So let's call G x1 G xn plus 1. So Cx divided by the Jacobian ideal, this dimension must be finite. And actually, this is the same as to say that, so since FAD is smooth, FAD, let's write G. So G is the same as G So this induces a variety inside Pn, and this is the same as say that this is smooth. So this comes from the singularity theory, and actually this is called usually Milnor vector space. But yeah, and so let me again recall C critical values of F, and we work to write it C1, C2, C mu. So let's say in this context, okay, F, remember that F is a C infinity fiber bundle over C minus C. What else? Okay, so what we proved at the end is okay. One notation. So L will be for me F equal to 0 inside C n plus 1. So maybe I make a picture actually. So this is my Cn plus 1. This is a Z, which is some copy of Pn, and what else? The whole space is Pn plus 1. So this is inside this one. Then I have my Y, smooth Y. And this one was X prime. And actually, if you look, then X prime is actually this variety that I expand is the projectivization of G equal to 0 inside this Z, which is the isomorphic to P n. And what else? Okay, so what was our main theorem in this case? So HQ, maybe I just write the, okay, HQ, so we just taking Z out, Cn plus 1, and here, so I call this one L. L is equal to 0 for Q. So Q not equal to dimension of the ambient space. Remember that now the dimension of the ambient is n plus 1. It is free for Q equal to n plus 1. Okay, so actually in this context, we are interested on the topology of this hypersurface Y, which has dimension n, and that's the reason we changed our notation from n to n plus 1 for the ambient space, so that we have n as dimension of Y. Okay, so this is let me see, and today we will see this free of finite rank, and we will see that it has to do with the Milnor numbers and so on. So, but let's for today start give some application of this one for the topology of hypersurfaces. So let's assume that we are interested to understand how big it is, the topology of this Y. And so since I have already I discarded the usage of X at Pn plus 1 from Now on, we will use X for this Y. So this means that X will be for me this F equal to 0 inside Pn plus 1. And so we discard the usage of X right at the beginning of our lecture. Okay, so let's a little bit analyze this statement. Okay, okay. Any question? Okay, so actually this is let me say one of the reasons that I wrote this, our main theorem, in a general context, was that I wanted Lefschetz pencil and this situation in the same context, because this kind of vibration appears also in the formation of holomicrofoliations. And yeah, but anyway, in this course we will be interested on the Hodge theory of the hypersurface, in particular the Hodge conjecture for hypersurface, which is still is a big challenge. Okay, so let's go to the application of this. Okay. Okay, so now I want to understand the topology of hypersurfaces. Maybe once again I write, so L was a affine subset of X. X was inside Pn plus 1. And let me, let's write long exact sequence of the pair L inside X. Okay, so let's well, I will start slowly using homology, despite the fact that I started the course with check cohomology. But anyway, if, as I said, you may just take dual and maybe you write our rational coefficients, and then just the direction will be changed. So let's HQL. We have an inclusion map, HQX, and then we have this HQXL, and then, okay, so it goes further, then HQ minus 1L, and here we have HQ plus 1XL, HQ plus 1 X, and so on. And okay, so by Leray-Thom-Gysin. By the way, in the literature, you just have the Geisin for the sequence, but let's call this Leray-Thom-Gysin. So this is so L is of course so let me say, maybe I have the Y is the complement. Now I'm making new definitions. So Y is not the previous Y. Y is the complement of L in Y. So this is actually our previous X prime. So this is a hypersurfaces in Pn, maybe old X prime that we had. Maybe if you want to make if I want to make a picture, then I had X, I had this Y is so I had this Pn. Everything is right inside Pn plus 1, and here this affine part is, I have called it L. anyway, let's go further. So L is so Y is of codimension complex codimension 1 in X, real codimension 2. So remember that Leray-Thom-Gysin isomorphism saying that Q plus 1 minus 2 codimension become Q minus 1 of Y. So this is HQ minus 2 of Y. And so we get this, let's say, what is known as a Geisin sequence. Well, but usually the people write in cohomology. So let's write it again. HQ plus 1x, HQ minus 1y, HQL, HQX, HQ minus 2y, and HQ minus 2y. Okay, so so we have this sequence. So let's do so remember now what Q. Oh, sorry, there is a L here. This is L. So oh, I think I forget to do okay. Before proceeding further, I had to write actually another long exact sequence. Remember that our main theorem is for the moment is this one, HQCN plus 1 L is 0. So maybe before I write this one, long exact sequence of L inside Cn plus 1. So then HQ Cn plus 1 L, then HQ minus 1 L. I'm writing everything in homology. HQ Cn plus 1, and here also HQ minus 1 Cn plus 1. So so but we know that this is 0 and this is 0 if what? If Q bigger than equal to 1. And what is the moral? What is the moral of this? So when Q is bigger than 1, this is an isomorphism. So this means that at the end of the day, we have proved that HQ minus L is this one. But remember that this was 0, and so let's write this one. So the conclusion would be that HQ minus 1 L is 0. So for Q equal to not equal to n plus 1, and it is free finite for Q equal to n plus 1. And okay. And maybe if you want, so this is, and remember that n now is a dimension of L. So if you want, you can write it in a better way. Then so this is just put it here Q, and then this is Q equal to not equal to n. So Q. So the affine hypersurface L has cohomology just in the middle dimension, in dimension n. Apart from this one, it has no cohomology. And actually, I have to be careful a little bit because in dimension 0, maybe okay. So maybe I have to be careful here. That if I want to proceed with the further, Q is not 0 because in 0 dimension, in Q equals 0, it is it's a copy of Z. Okay. Anyway, our main theorem can be translated into to the cohomology this affine hypersurface. And this is one of the reasons that really I put some emphasis for affine varieties in my book, because first we capture the topology of affine varieties, and then we go and we capture the topology of compact varieties. Okay, so now I am already done with this this one. So let's return back to the long exact sequence that I was writing. So now the point is that now this guy, we know the topology of this guy. All the cohomologies are 0 except the middle one. So let's just try to write this one. So if so this is 0 and this is 0 if let's say this is Q not equal to n, and this is for Q minus 2 not equal to n. At the end of the day, what I have, let me say in this way, H okay, it's Q. Okay, so Q, maybe your Q not equal to n, and actually I have to be a little bit more careful because of this dimension 0, but okay, n and n minus 2, then HQX is isomorphic to HQ minus 2y. This isomorphism here. Well, there is this plus 2. I am making yeah. Okay, so let me make a consequence, and maybe I take just Q below the dimension Q less than n. I have HQX isomorphic to HQ minus 2y, and now I can use a kind of induction. So remember that n is dimension of x, and what else? Then y, x is a hypersurface in P n plus 1. Y is a hypersurfaces of Pn. So this means that if I proceed further this isomorphism, and then replace the role of x by y and so on, at the end of this will imply that HQ of x, but let's say for Q less than n, it will be 0, 0, odd, Z for, well, let's say Q odd, Q even. And why this one? The reason is that I will, as I said, I will replace the role of, I will replace the, what, let me say, now I will, y, I will consider y as x again, and I will repeat this isomorphism. Maybe in this case, I have to, let's say, HQ x isomorphic to HQ minus 2, let's say x1. So now this x1 is y, and now I use x1 as x and go further. So the point that when Q is each time the dimension and homology is dropped by 2. So if Q is odd, I will at the end I will get into negative numbers, and then the homology will be 0. And if Q is even, then at some point I will get H0 of some xi. So x1 is a hyperplane section of x, x2 is a hyperplane section of x1 and so on. And the main point is that this dimension of xi is strictly bigger than 0, because in dimension of y will be dropped by 1, but dimension in cohomology is dropped by 2. So I will not reach H0 of some zero-dimensional variety, which might have a z to the, this guy must have many connected components for in dimension 0, and this might be in z to the some power. Anyway, then I will reach to this part. So maybe one consequence of this statement is that below the dimension n of hypersurface, we have just let's say cohomologies for Q even, for Q odd there is no, and then by Poincare duality we can go it further. But I'm not going to focus on this one. Actually, if you want to use Poincare duality for this one, for Q, maybe make a comment here. Q for bigger than n. I will not focus on this one, but at the end, this is true. 0 Q odd Q not equal to n, and z Q even Q not equal to n, and Q equal to n, that now we are going to discuss further. So let's go back to the Q equal to the n case, and this is really the focus of our attention, because in Q equal to the n there is some non-trivial cohomology going on. So let's write down this in Q equal to n. So I am going to write down this this cohomology for Q equal to n. So let me write down. So it was HNX going to HN minus 2y, and then HN minus 1L, which is 0. And from another side, then this is HNL, and then HN minus 1y, and then HN plus 1x. And then like the other one, there is this HN plus 1, HN plus 1 of L there, then which is this 0. Anyway, our the trivial part of our cohomology is HNX, and it's a kind of natural because it's a fine subset, is non-trivial and has a big rank. And so this short exact sequence tells us how big is this HNX. Maybe let's our main attention is okay. Our main attention is n. It's the case of n in even. Let's see. In the case of n even, so HNL, maybe write HNX, and then n even. We saw that this these two guys are 0 because the n plus 1 and minus 1 is also here we have 0. And then we have this HN minus 2y equals 0. So if you want to write down in cohomology, just change the direction and put these indices up. And by n minus 1 dimension of y is n minus 1. So this is by previous argument, this is z. And you see that the topology of the hypersurface is just a little bit different from the topology. It's defined by some rank one Z module, and oh, sorry, there I have missed H and L. There is H and minus 1 is missing here. Okay, so anyway, what I was saying that we can capture the cohomology of H and X by this. You you see that this map is almost surjective, except in just some codimension 1 let's say, except by some dimension 1. And the kernel of this map, it comes from homologies of Y. And let me say something. Usually, let's say primitive, let's say homology. In this case, homology. You can define it also in the cohomology. H and X. In my book, I put 0. Sometimes the people will put prim for primitive. Is just the kernel of this map, and what I said, this guy is inside H and X, and it has the codimension 1. Okay, so you see that if we have a good understanding of H and L, then we have a good understanding of how big is this H and X also. Okay, so let's return back to chapter 6 of my book. So so something that now I am going to tell a bit that this H and L is actually generated by this is called vanishing cycles and so on. And at the end, if we have a basis of this guys, in order to understand the basis of this guy, we just project the basis of this guy here. Okay, there will be some relation, linear relation between the basis of this guy projected here, and this relation has to do with the cohomology of Y. Up to these relations, we capture basically everything. Just one element will be missing in H and X, and this is the element that maps to something non-zero here. But slowly, when we go to study the Fermat variety and so on, we will see, we will get familiar to this, to have to understand the topology of X by just knowing the topology of L. Okay, so. Any question? Okay, so let's. So now what I'm going to do, I am going to a little bit recall again the proof of the main theorem, because I want to remember this concept of vanishing cycles and Lefschetz thimble and so on. So let's go to chapter 6 of my book, a window. Okay. 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 So during the proof of our main theorem, I just try to simplify a lot of arguments and to put in the trash a lot of blah 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 which were not necessary for the proof. Okay, so something that I told that at the end, the Hirschman's vibration theorem is the main theorem that it enables us to see that the fibers, from a map we get a fiber bundle map. Maybe actually before proceeding further, I tell one consequence of this this theorem. Okay, let's maybe just okay, maybe very fast. Vibration theorem implies okay, all smooth hypersurfaces of degree d in Pn plus 1 are diffeomorphic to each other. Okay, of course, in diffeomorphic for me means in the category of let's say C infinity function. So this is a kind of nice observation, because this means that at the end of the day, from the topological point of view, there is no difference between just let me say in this way, just the degree and the dimension of the hypersurface classify it. So the reason is that, let's say, maybe a sketch of the proof. I put the sketch of the proof. Good. So T, let's say T. So let's just polynomials of degree D, homogeneous polynomial of degree D. So this is their homogeneous polynomial of degree D. So in this context, x is x0 until xn plus 1. I switch the usage of x for x1 until x plus 1 and x0 until xn plus 1. So in this case is x0 until xn plus 1. So this is parameterizing smooth hypersurfaces of degree D. And then so this is basically, you can see that this is TCX D minus something called discriminant. So there is some variety of this is a kind of affine space, and there is some variety which is called discriminant. When discriminant is 0, the hypersurface is singular. Anyway, so the proof will be the application of a Hirschman thread. In which sense? So we consider, let's say, this variety x, calligraphic x, which is x and t in Pn plus 1 times t, such that maybe I write it as f, let's say f. So such that f equal to x equal to 0. So f is the polynomial of degree D, and x is a point in Pn plus 1. So this equation is this one, and then we have this projection in T. So again, so this will finish the proof, knowing that T is a connected connected smooth manifold. Actually, it is a affine variety, irreducible affine variety, that it will follow that it's a connected another time. Then this P is a submersion. And you just calculate the derivative and you observe this one. So you will see that this is a submersion. We have already cut out the singular fibers, which corresponds to singular hypersurfaces. We will have a submersion, and its fibers are just hypersurfaces. This is a proper map, and according to Ehrenschmann's fibration theorem, this is just a locally trivial fiber bond. And yeah, maybe to see the things in this way, maybe it is better than considering just the Lefschetz pencil. So let's go to any question. Let's go to the book again. Okay. Okay, so this is, and I told that there are versions of these other versions of Ehrenschmann's fibration theorem is important when there is extra manifold and or when there is let's say manifolds with boundaries. Actually, this was also used during the proof. Okay, then let's proceed further. Something that I used I didn't prove actually that this was this theorem which comes from a very old text of Steenrod. Remember that whenever maybe in our context, let's say, maybe just a moment. So let's say, remember that in our context we have this C. So let's say this R, S, B, everything here are subsets of C. And we are avoiding the critical values of F. Let's say there was this C1. Okay, this is my C2, and so on. So that is this argument of lifting a retraction. So we have this, we have local C-infinity locally trivial fiber bundle. We were using this homotopy covering theorem that whatever contraction that we have in the base, okay, maybe I have not explained the notation, but remember that we have a kind of contraction in the base in the image of this F function, and we wanted to lift it to fibers, and this is taken from this reference. If it is a purely topological statement, so we use this. Okay, and actually we used it in many places during our main theorem. Okay, another byproduct of our study is the concept of the monodromy. Let me explain this one in paper. Okay, I will explain this in paper. Okay. So monodromy. So just very fast. So again, we had the C, C1, C2, C mu. So the idea is the monodromy is just, let's say, take a B regular value, B regular value. So the idea of the monodromy is also simple. And if we just imagine that we are taking a very pass from B to another point, let's call it B tilde. At the end, that B and B tilde for me will be the same, and comma a path from B to B tilde, avoiding this critical value C1, CMO. So again, I will explain that in a more intuitional way. So we, by trivialization of our fiber bundle, if we know that this is let's say LB C infinitely is the same as it's a nearby point. So we can cover this path with this trivialization chart for our fiber bundle, and then in the intersection we can choose let's say I choose B1 here, B2 here, B3 here. So let's say let's call it the image of gamma is inside U1, maybe U is union I equal to 1 until M UI, and let's take BI inside UI intersected with UI plus 1, and then B let's say B0 to the B and B to the B, let's say B1 equal to, and the BM becomes B tilde. Anyway, I'm just taking points in this intersection, and so on. So what I wanted to say that at the end, LB is isomorphic C infinitely to LB. And remember that L, these are the fibers. LB1, LB2, and then LB M, which is the same as LB. And the idea of so this C infinities maps depends on our trivialization, but if we pass to cohomology, let's say, or homology, then we will get the HQ LB HQ, which is L tilde, LB tilde. Remember that Lx is f minus 1 x, and maybe just consider my classical context. If this f is the map from Cn to C, the polynomial map. So we get this isomorphism, and what we can we can check that all these C infinities are homotopic to each other. So let me say all these let's say C infinity maps are homotopic to each other. This means that when I'm in a local chart, I choose, I use trivialization, and I find this map. This will, whatever trivialization I use, the obtained map, all of them are homotopic, and for this reason, they induce the same map in cohomology. So these are some details that I think in your way to understand the things, you can convince yourself that really these things are happening. But what I'm saying, that then one gets a map H gamma from HQ LB to HQ LB tilde, and something that one can check, it only depends on the homotopy class of gamma. And what I mean by this one, okay, so I had the B tilde, I had Just a moment. Oop. I had a B tilde, I had B. I have to avoid C1, C2, and so on. So this means that if I do homotopy from B to B tilde, but again, the homotopy in, let's say, C minus critical value, because these critical values are atypical, and I don't have trivialization of my fiber bundle there. And so at the end, this map will not be depend on the homotopy class. So finally, we reach to the monodromy group. So when B equal to B tilde, at the end, we reach to this map P1 C minus C, the homotopy group of C minus C at a point P, and then HQ LB going to HQ. So we have this monodromy representation. So if you have a pass gamma and the cycle here, then this just goes to this H gamma, H gamma delta. And the concept of monodromy groups will be important for us. And okay, let me say what time is it now? It's any question? Okay, I have maybe some more 5 minutes. Let's talk about this vanishing cycles and thimbles. I wanted to do more algebra from next week. Present now, window. So let's go to the game my book. Okay. So as the picture that I explained here a little bit, I have explained in a more general context. This N was N, the submanifold N in Ehrenschmann-Fibrecher theorem. But at the end, the basic idea is the same. If you want to read this part and see that at the end, the ideas are very simple. So here, this our monodromy representation, P prime being C minus C. And the point is that, something maybe I just a little bit explain on this this picture. So the point is that when you turn around a typical fiber, let's say fiber over C critical value of F, really this H gamma, let's say this, let's call this pass gamma, and then we had this map H gamma, which were acting in the homology of our fiber. And when you turn around the critical values, this map might be a non-trivial map. This means that a cycle in homology, after traveling on top of this gamma, may return back to a cycle in the original fiber, which is not the previous one. And this is the basic idea of Picard-Lefschetz theory. For those people who know Morse theory, which is actually kind of more famous in topology than Picard-Lefschetz theory. In Morse theory, usually instead of the image, which is in our case is C, we have real numbers. And so the real numbers are one-dimensional. So then the critical values of your function are just points on a real number R. And if you remove the critical points, then the real number will be disconnected. This means that at the end, when you want, in the Morse theory, when you want to cross from one point here, when you start from here, you have to necessarily cross the critical value, and when you cross it, the topology changes. But well, let's say the complex version of Morse theory, which is older than Morse theory itself, instead of crossing the critical value, you just turn it around, and your varieties are complex. And the topology doesn't. The topology of your variety is fixed, but the maps that you get are in homology. They are not identity. And so just remember that Picard-Lefschetz theory is the study of topology of the fibers when you turn around the critical values. Okay, then there are a lot of other blah, 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 which I have tried to write in a more general context. Maybe this concept of vanishing cycles that at the end it popped up in the proof of our main theorem. Okay, maybe this one, maybe I explain this one, and then I stop the course here. So maybe I will write more 5 minutes in the paper, and then okay. 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 So again, for simplicity, take our C-plane, take a B, and retake one of these critical values that we had. And okay, one of the figures that we used, this was this taking a disk and then connecting B to C. In our context, even you can let's say you can even go directly into C. So C a critical value of F, and maybe for simplicity, again, this is again for simplicity. For simplicity, assume that F minus 1C has only one non-degenerated singularity. So maybe I make the picture again. So we have this fibers over this one. So let's actually make the picture over this one. So let's say I think I will make a one-dimensional picture of this. No, that's okay. Okay. So our B, I had, let's say, LB. And maybe just I will draw it LB as circle. And okay, so let's and our C, it is I have the singular fiber. I want to make it okay, maybe be becoming like this. So maybe let's make a different picture as not the same one as in my book. So just so the idea is that when you are B, you have still a smooth manifold. They are the same. And in this case, I have put a circle. And when you go to C, your variety will be singular. In my case, the circle has changed has got some node. And this infinity shape or 8 shape picture. And also it's non-degenerated, so this means that here F looks like, so this F equal to x1 to the n, x1 to the 2, x2 to the 2, then xn plus 1 to the 2. So the ambient is been okay. Something that we learned in our on the proof of our main theorem was that in this context, let me see if we can make it better. Okay. Anyway, so if you are near, let's say, if you are near to C, what we described, let's say, this delta hn plus 1 L D L B L actually for B near, maybe let's go B till near to C, and then its boundary delta here hn lb. Remember that in proof this we found it after making this this local coordinates. So this look like means that in a local coordinate, in a local holomorphic coordinates. So these are not the global coordinates of our ambient space. If you want to be, if you get confused, maybe just put a y here. Okay. And this was just this this ball, be an n plus 1 dimensional ball, and this was just it's a sphere. And at the end of the day, we have this this delta for B till near B. But I told that we can by monodromy we can transport it to the fiber over B itself. Well, if you want to make a kind of picture, maybe I'll just show you the picture in my book and then finish the course. Okay, so okay, maybe let's say. So maybe exactly this picture might be a better way to see this this vanishing cycle. This picture appeared in our main proof, and this Bn and this, well, actually there is a mistake here. This is Bn plus 1, and this is Sn. And then this is a kind of embedded in our picture. The boundaries of these balls that we take, they are in the fibers, and they are vanishing. Let's say they are spheres, which we call them Lefschetz vanishing cycles. And but what I want, where I want to reach, I want to reach to this picture that I made. Exactly this picture. Let me explain a little bit this picture and finish the course. So we were our B, we have a smooth variety LB, and then we connected to C1, C2, and C4 until C mu. And so the idea is that we can transport all these spheres near to CIs to here. You see, and you see that in CIs, these spheres, they becomes a point, and that's why they are called vanishing cycles. And so you can these points are actually the singular points of your function f. And so you see that from 0, from point, it starts appearing S-spheres on the fibers, and one can transport this S-spheres here in your main fiber, and the same where over here, over this path. So this is over this one, we have this one, over this one, it's happening this one, and this is our, let's say, this one, and then this other one, our this one. And remember that in my main examples, F from Cn+1 to C, I claim that it's a free of rank a finite rank, and it's free, and actually we know it's generated. So actually the generators of Hn of LB are spheres. And this is a kind of stronger statement. We have a basis of HNLB by spheres. And yeah, I think I am done for today. So maybe something that I would do in the future, if to put some informal discussion session, and if you want to discuss further details. But for me, the topology is a matter of just one trying by himself to observe that really the things are rigorous, not loose. Okay, I am done for today. So let's okay.